Good morning, everyone, and welcome to the 2017 Royal Tyrrell Museum Speaker Series. Today, the Royal Tyrrell Museum and its cooperating society are proud to present Dr. Glyn Williams-Jones. Glyn is an associate professor of volcanology in the Department of Earth Sciences at the Simon Fraser University in Burnaby, BC. Glyn is originally from Montreal, Quebec. He obtained a bachelor's degree in the Department of Geology at the University of Montreal and decided to stay in the same department to pursue a master's degree in volcanology. For his thesis, Glyn studied gas geochemistry of Arenal, one of Costa Rica's most active volcanoes, in order to monitor changes in explosive activity. Subsequently, Glyn moved to the UK to pursue a PhD in volcanology at the Open University in Milton Keynes, England. For his PhD, he used gas geochemistry and geophysics to determine the likely cause of fluctuations in volcanic sulfur emitted by the Masaya volcano in Nicaragua. After completing his PhD, Glyn moved to Hawaii to hold a postdoctoral fellowship at the University of Hawaii at Manoa, where he applied the same techniques to better understand the long-lived activity at the Kilauea volcano. Finally, in 2003, Glyn joined the faculty team at the Simon Fraser University and since 2012 has acted as Volcanic Situation Duty Officer for the Canadian Hazards Information Service of Natural Resources Canada. Glyn's research interests involve geochemical and geophysical modeling to investigate the processes responsible for triggering volcanic eruptions as well as those controlling persistently active volcanism. Today, Glyn will talk about Canadian volcanoes, specifically evidence for both historic and current volcanic activity in BC. So, without further delay, I present you Dr. Glyn Williams-Jones.
Thanks, Russell. Well, thank you. Thanks for having me. And this is quite fun because it's payback for Francois. He gave me and my family some backstage access during the summer, and my boys just had a field day here. So I absolutely just jumped at the opportunity to come and talk about some Canadian volcanoes. It's one of these things I've done most of my career in Latin America, Hawaii, Southeast Asia, where everything's going boom and it's popping off regularly. And we didn't really think about, well, what's going on in my own backyard? And so over the last few years, I've started to be able to get involved in some projects closer to home. So hopefully at the end of today's presentation, you'll walk away and you'll realize that yes, in fact, unlike most Canadians, you do now know that yes, we have volcanoes in Canada. They are active, and some of them are even currently active. So we'll get going here. Now, we'll just do a very small crash course, drill back to your high school science. Basically, on Earth, we have a series of plates. So we have this idea of plate tectonics. The only planet in our solar system where we've got a continuous dynamic movement of plates. And obviously here's the Pacific, North America, and that movement of plates, of oceanic plates and continental plates, leads to big mountain chains, say in the Himalaya here, where India is smashing into Eurasia, leads to very large earthquakes, what we're waiting for on the West Coast. And broadly, it's all driven by convection, the mantle of our Earth. I like to think of the Earth as an avocado. We have a very thin crust, very brittle crust. We've got the nice tasty stuff in the middle. That's our mantle. And at the center, a solid core. There's more details, there's more caveats to that, but the mushy, tasty bit is what's convecting and turning over geologic timescales and driving ocean, in this case, ocean crust interacting with continental crust. And it's important to sort of get into mind, when we're thinking about geologic timescales, the movement of the plates on Earth are incredibly fast. Maybe maximum 10 centimeters per year. By geologic timescales, that's very rapid. But it builds up, and eventually, especially on the West Coast, where we have the Juan de Fuca plate subducting underneath North America, that interaction, when we get the stress buildup and eventual release, we can have significant energy release, form of earthquakes, but also, what we'll be focusing on today, we have the generation of volcanoes. And most people are aware, they've heard the term the Ring of Fire. So all the way around the Pacific, 2/3 of the world's active volcanoes under air. There's thousands more underwater that we have very little information about. But 2/3 of the world's active volcanoes are around the Pacific because of this subduction-related process. Of course, there are some oddballs where I spent a year and a half in Hawaii, pop out the middle as a hot spot volcano. But we'll be focusing in on North America. I'm heading down next week, back down to Nicaragua in Central America, and I've also got a project now in Ecuador and Chile. So looking at these subduction-related volcanoes. Those are the styles of volcanoes that we're going to be looking at today. Similar chemistry to Hawaii, but a different style of volcanism. So in Canada, on the west coast, we've got lots of volcanoes. Their activity is different to what we see to the south in the US. The levels of activity are much lower. We don't see the classical, beautiful, inverted ice cream cone, Mount Fuji style volcanoes, in part because of glaciation, just weathering things down, breaking them down. But we have those volcanoes. And the ones just sort of marked here, especially the dots, not sure if you can see the triangles. Triangles are the more geologically recently active ones. But all of these have been recently active, the last 2 million years or so. So again, geologically, very, very recent. And from a hazards perspective, what we really want to do is look at those that have been most recently active, at least in kind of the human time scale. And today what we're going to focus on, there's 2 volcanoes, 2 different belts. The first one we'll start off with Siax, is part of the Northern Cordillera and Volcanic Province. So this is right at the base, just in northwestern BC and running all the way up to the Yukon border. And then we'll pop down back closer to home for me into the northern extent of the Canadian Cascades, and specifically Mount Meager. So most people in Vancouver, on a clear day from Simon Fraser, we can see beautifully Mount Baker, beautiful conical volcano, and many people just think, oh well, the volcanoes stop at the border. Well, volcanoes really don't care much about politics, and so the system does carry further north, and so Mount Meager is a system that is important because of its proximity to Vancouver, in the Lower Mainland, and its relatively recent activity. So CX volcano, I'd never heard of it before 2 years ago. It's an innocuous little volcano, what we call a polygenetic cinder cone. It's only about 100 meters high, this tiny little thing, and only maybe about 500 meters in diameter at most. We think, there's very, very little work has been done here, but we think there's possibly 1, maybe 2 eruptions, the most recent in the 1770s, and this was done largely with carbon-14 dating. A lot of detail to be done, and really it's the work of my PhD student, Yannick Lemoine, from France, who's really focusing in on the detailed geological mapping to pull apart the story of this volcano, to figure out, well, what the heck's going on? What is special about this volcano? Small crater. Here, what he's developed is a 3D computer model based on with digital photos. There's the cone, and there's a little baby one, even smaller still. Currently, we haven't named it properly. It's just a parasitic cone. But Yannick has been doing the detailed hard work and all the mapping. So this innocuous little volcano, well, why do we care? Why is this even remotely important outside of just an esoteric academic exercise? Well, in part it's rather odd. We have this tiny little volcano that was the source for an extraordinarily long lava flow, 32 kilometers in total length. Fairly voluminous, almost half a cubic kilometer of lava that flowed out in essentially one event. Now, I said it's not exactly the same style of activity as Hawaii, but we do see very, very similar features. Classic lava tubes where channels form, a crust builds over, that solidifies and now keeps everything hot, and we channel the material to fairly significant distances. Very flat, almost plate-like lava. It's called pahoihoi, the Hawaiian term. So very smooth. One of the things that stands out is everything's covered in moss. So you have to sort of pull things back to get a clearer view. One of the grad students that we were working with from UBC, Alex Wilson, is showing a beautiful tree mold. So here we've had very fluid lava flow around a tree. This would have been heavily forested at the time, and basically form a mold around that tree, collapsed, the tree burnt out, and we left this beautiful mold. And if you look on the inside of that mold, you can actually see remnants of the tree being carbonized, and you see a little pattern of material. Some people initially thought was the bark itself, but it was actually just as it's turning into coal. So there's an odd system here. Again, this could be just something very esoteric. It's just, tick a box, better understanding of something in our backyard. But as a volcanologist, for most of us, it's always in the back of our mind, or ideally in the front of our mind, what's the impact on people? What is the hazard of this event? So looking at the volcano, and specifically based on the oral histories, the oral stories of the Niska people, we know that lava flowed down sometime in the 1700s. We're starting to zoom in. But it started to flow down from this cone, dropped about 400 meters of elevation, ran into the NASS River valley, flowed north, again still staying very tightly constrained, and then as it came into the NASS River valley and the floodplains, it flared out and formed this large lava delta. Now, really importantly, that lava flow destroyed two villages, the Laxkavit and Kisiluks. I'm not pronouncing this properly, unfortunately. Niska is quite a difficult language to pronounce effectively. But more than 2,000 people died in this eruption. This makes it one of Canada's worst natural disasters. And yet very, very few people are aware of it. You ask anyone in BC, they've basically never heard of it. So there's something special here. Why does this innocuous little volcano create a lava flow? And I'll tell you right now, most lava flows you can outwalk. They're not dangerous. They're destructive, but they're typically not lethal. And yet, here it was responsible for well over 2,000 people being killed. So this is something that really drives it. And if it only erupted in the 1770s, could it erupt again? That's always looking forward, something that we want to be keeping in mind. So, being a very young province, there was one written record that we might be able to link to this event. A young lieutenant, Spanish lieutenant, Juan Francisco de la Bodega y Cuadra, was on a Spanish schooner coming up from New Spain or Mexico, and March 1775. They anchored here in Alaska, in Bucareli Bay, and report seeing or feeling very pleasant temperatures, which they immediately linked to large active volcanoes, but also perceiving a glow in the sky. Now, it doesn't surprise me that they're thinking about large volcanoes. They've just come up from Mexico, where they've been seeing things like Popocatépetl, Colima, very large volcanic systems. But in reality, if SEAX was erupting, sending lava potentially hundreds of meters into the sky, 290 odd kilometers away, you're not going to see that. You're not going to feel the heat from that. But perhaps the glow of that event reflecting on, say, mid-level clouds, that we might be able to make a linkage. So this is a very tenuous link. But that's all we had in terms of direct written records. However, it doesn't mean that there wasn't observations being made. And the difference is that the Niska people recorded it in a different fashion. There was detailed observations, but recorded through oral histories and stories passed down from generation to generation. And this event had a fundamental impact on their culture and society, and it continues to do so today. So the story tells of some young children who are on the edge of the NASS River, and they're tormenting the salmon, cutting the backs of the salmon open and placing flaming sticks and then releasing them, or putting fragments of shale in and watching the salmon turn over and spin around in circles. Now, as you're aware, especially on the West Coast, salmon is fundamental to the vast majority of the indigenous cultures of the Pacific Northwest. And so to do something like this really is completely outside the norm. And as with many indigenous communities, the NASS River is extraordinarily rich in terms of food supply, and the microclimate is such that it's very, very temperate. But nevertheless, there is a strong taboo in the Niska culture that you only take what you need and you use what you take. You do not waste food. You don't waste that resource. So it's understandable that something like this would have a marked impact on their culture and would be sort of carried through through the generations in the storytelling. The fact that they speak about salmon suggests that we're probably dealing with July to August when the pink or humpback salmon spawn. And this is the kind of thing that you see in the NASS River on any sort of shallow areas. The idea that it is a humpback potentially could be linked to this idea of placing shale in the back and causing a hump on the back of the salmon. So there's some interesting details in the stories that we can try to extract to make the linkage with the modern sciences. So these little brats are tormenting the fish, and an elder comes along and says, look, you need to stop this. The salmon will curse you and the creator will be angered. And unfortunately, as many children do, they just tell him to go away. And lo and behold, the creator is angered. And smoke and steam and trembling ground is reported. So scouts from the two villages are sent south to a ridge, Genwanax, just across the Siax River, looking up towards the volcano. And they report seeing smoke and flames, maybe a tongue of lava from some type of a spirit or fire beast. Again, there's details in there that we still need to look into. They run back to report their observations, and many villagers fled. Others ignored it. You're just, the sky is falling type response. Those that were able to canoe across the river were saved, but many, many people died in this event. So as the lava is flowing down and starting to really pool around the river, the NASS River, a local spirit, a mountain spirit, goes and wakes up his friend, Guatzak, who is a very powerful being, who is a protector of the Niska people in this area. And so his friend says, look, you've got to get on, your people are being threatened. And so this battle ensues between Guatzak and this lava spirit or the lava flow itself. And over many days, he's reported to be blowing on the lava flow with his nose. So this mask, actually, the nose will extend and retract as sort of showing this part of the story. So they fought for many days, and the lava eventually cools in this very straight margin. Obviously, there's been some erosion. The NASS River is an important river. There were reports that this part could have been almost a lake, so maybe some kind of a marshland environment on the edges of the floodplain of the river. But again, we've got these interesting details that we can pull something out of. So my grad student and one of our field assistants, they rented a boat and went up and down the NASS River with making video and building three-dimensional models of this wall of lava that is being cut through. And again, on top, it's extraordinarily smooth. And on the margins, we see some of this area is maybe up to 10 meters, 15 meters thick. And some interesting geological features start to jump out. What Yannick has modeled, or mapped rather, here are what are called pillow lavas, specifically radially jointed pillow lavas as we see here in close-up. So if you think to the Hawaiian videos that we see on TV and on the internet, where lava is entering water, there's a beautiful video right now online where it's just this fountain going in. But when it goes into the water, that lava quenches instantaneously, forms a balloon or a bubble shape if the conditions are right, and that will inflate and eventually completely solidify. If the conditions are right, we can get cooling all the way around, and these joint sets, they're called columnar joints. The joints are always perpendicular to the cooling surface. So what we see here is we've got cooling all the way around, and these cracks, these joints, all propagate inwards towards the center. Now, some of these are 2 to 4 meters in diameter, very, very large for bubble or pillow basalt standards. I was sending these images to my friends in Hawaii, and they were blown away by the size. So, innocuous little volcano with a very big lava flow, a normally sized pillow basalts. There's something really interesting going on here. Working in this environment, trying to make the linkage between computer-assisted modeling versus the oral histories, these observational data, can be tricky. In this situation, different parts of the story belong to different families within the community. So there's discussion on who has the right to tell which part of the story. There's debate amongst the different families on aspects of those stories. There's actually a linkage between the ownership of that story and ownership of land, of property. So these are things that we have to be very sensitive to, and this is why it really, this is a true collaborative project with the Niska government and the House of Knowledge, their university. So ideas, if we can start to extract this information and make sort of heads or tails of the details, do we see eyes of that spirit beast, that lava god or whatever it was? Does that relate to the main cone being active at the same time as this little parasitic cone? It's quite possible. So these types of things I think are really quite exciting. But really it's Yannick, my PhD student, who's drilling in and making the detailed mapping, trying to see where are there different textures and fractures where lavas could have come out. But we're also trying to understand, well, what was responsible for these fatalities? Could it be huge amounts of gas, carbon dioxide, which is denser than air, can flow down valleys, some great distances? There's been some impressive examples in Alaska, multiple kilometers. Could it be volcanic smog, that lava entering the river, causing very acid gases to steam up and out? And again, Hawaii shows beautiful examples of this that people could have succumbed to. So that's a plausible option. I think it's also plausible that those lava flows could have triggered very rapidly moving forest fires. And we know here in Alberta recently the scale of these events. and how fast these forest fires can move. So easily catching people unawares. So really, we're at the early days of this study. Yannick's detailed mapping is also finding some interesting, what are called lapilli, sort of sub 2 millimeter, 2 centimeter grains of volcanic material. So this red stuff here, very oxidized, iron-rich, essentially rusty material, overlain by black. The same material, but very, very glassy. Two different horizons, different events, maybe within the whole same episode. So lots of details are coming out. Some very bizarre material that I've never seen before. Pelleys tears are normally tiny droplets of lava that are ejected. Pele, again, the Hawaiian goddess of volcanoes. But these seem to be what we're calling Pelleys bubblegum. They look like bubblegum that you've blown up and stuck outside in the winter and allowed to freeze. That's what it looks like. These are a few centimeters in diameter. Some of them are up to tens of centimeters in diameter. And we don't understand how they could form. Were they droplets of lava that landed on the flanks of this little cinder cone and then continued to inflate? It's hard to work out the physics on that. Or did they travel already as a frozen blob of bubblegum and then land and yet not be destroyed by more material raining down on it? So a colleague at the U of A is actually scanning, doing a CAT scan on a number of these samples for me to try and get at the internal structure of these. So that's a little side project. But the fun thing about these types of studies is you stumble on things that you were never expecting, and it takes you down an avenue. The other thing that is really neat, and it tells us something about the volcano itself and the fluidity of the lava, is we're finding volcano snowballs. These accretionary lava balls, this one is about just under 0.5 meter in diameter, and essentially what it represents is clots of lava, larger pieces than this, sort of, in this case, maybe fist-sized spindle bomb ejected out, landing on an open channel of lava that is flowing, and then it starts to roll. And I'm not sure how well you can see it in the back, but it's very much like making a snowball for a snowman. So you take that part in the middle and you roll, and it keeps gluing more and more material on. Kelly, my friend and colleague at UBC, that one is 3-4 meters in diameter. And Yannick has now mapped at least 80 of them all down in this area. So it's telling us that there was a big open channel that was flowing vigorously, and it was very low viscosity material, very fluid lava. So some details that are starting to come out. If we now stand back and move further south, a very different style of volcanism. Rather than this innocuous little baby volcano, we're looking at a big monster. It's a volcanic complex. Mount Meager, it's the Mount Meager volcanic complex, just 60 kilometers northwest of Pemberton, or about 150, 160 kilometers north of Vancouver. It's been going for about 2.2 million years. A large massif of overlying volcanoes, volcanic centers, and where we'll start to focus in is in the central area within the Jobe Glacier. But as I mentioned, it's part of the northern extent of the Central Cascades, although there's some recent studies that suggest it might be actually a separate thing. We're going to lay ownership to the Canadian segment of the Cascades, and we'll say it's different just for the heck of it. But just to give you a few names, there won't be a quiz at the end of this, so don't worry. But there's Mount Meager proper, but the whole complex has got a number of peaks. Plinth Peak, we'll see, is where we had the most recent big explosive activity down this valley. And there was a huge landslide that we'll touch on, came down Capricorn Mountain around there, and then the recent activity in this central area. I'll bring this back as a reminder. So, very, very briefly, very long-lived system. As I said, 2.2 million years to present. Lots of overlapping, heavily glacially eroded material, rotten material. over that time period, we've had 2 million years of acid volcanic gases fluxing through the system, weakening the rock, and just also extensive normal weathering that we get on the Pacific Northwest. We know that it's broadly been active because, well, there's extensive hydrothermal systems, hot springs, all around Mount Meager. They were doing, for many years, geothermal exploration as a heat source, energy source. And you can go into the Meager Springs. And, that's not me, unfortunately. But especially when it's nice and snowy, appreciating this kind of thing is interesting. Little do they know what is cooking up top. So this is Canada's largest recent explosive eruption, 2,400 years ago, give or take. And again, to put into perspective, that's about the same as what we saw the 1980 eruption of Mount St. Helens. So Mount St. Helens was about a cubic kilometer. Mount Meager, we may end up actually increasing this number a bit, but it's pretty darn close. And what we had was this large eruptive column sending ash and pumice and blocks, these ballistic blocks raining down, but potentially up to 15, maybe 20 kilometers up into the air. Simultaneously, those clouds often collapse catastrophically, and they form what are called pyroclastic flows. Pyro meaning fire, clast meaning fragment. So a fire fragment. So in contrast to lava flows, most typical lava flows, these dense clouds of glowing gas and ash will travel at hundreds of kilometers an hour, many, many hundreds of degrees Celsius. The most lethal volcanic hazard, bar none, on the Earth. There's widespread deposits of pumice in the area that's still actively mined. And so an important event. But these styles of volcanoes, in contrast to CX, where the impact was relatively localized, you get something going 10, 15, 20 kilometers into the air, you're going to have a broad impact. And in fact, ash from that event, it's called the Bridge River deposit, comes all the way out to Edmonton, Calgary rather, almost gets to Edmonton. And in fact, some recent work by a colleague at Douglas College, he thinks he may have detected some more material a little bit further south, expanding the area where we think there were deposits, upping the potential volume of material ejected. So just because something happens right on the coast doesn't mean that you guys aren't at risk. And it really depends on wind direction. So this is the small eruption, very small eruption of Eyjafjallajökull in Iceland in 2010. So things going on distally, we know, can have broad, even global impacts, especially in our interconnected society that we live in right now. So that big eruption column then transitioned into another type of lava flow, a very viscous, thick, stodgy lava flow that was starting to creep down the mountain and then eventually failed. It couldn't maintain on that steep slope on Plinth Peak. It broke up catastrophically and generated another type of pyroclastic flow, what we call a block and ash flow, bigger fragments, big, large car-sized blocks sometimes. But they flowed down off this steep slope into the Lillooet River Valley. And because of that confining nature of the Lillooet River Valley, it bulked up. Normally these would just flow out and that would be the end of it. But because it bulked up, it stayed hot and it was actually able to melt itself back together. So it welded itself and formed a 110 meter high dam of completely glassy, impervious or impermeable rock that then dammed the river and allowed the temporary formation of a large temporary lake, almost half a cubic kilometer of water. So this is really neat work by my colleague Kelly and his postdoc and grad students, looking at the geology and piecing together the puzzle pieces of what happened. They're now quite certain that it took probably on the order of 40 to maybe 60 days Here's our welded dam with loose, more pyroclastic material. The water fills up behind the dam, starts to saturate this loose clastic material, and eventually the whole system fails catastrophically as an outburst flood. In Iceland, these happen regularly, mainly underneath the ice sheets. They're called jökulhlaups. And it's catastrophic. You lose half a cubic kilometer of water in an instant. And so the erosive power is incredible. The modeling suggests that this slot canyon cut back 2.5 kilometers through 110 meters of completely solid material in 8 hours. So this is, biblical scale type erosive events. It's one of the neat things with geology is we started off with catastrophism. Everything happened in catastrophic events. We went to uniformitarianism. No, everything is slow and steady, and it's the same as the past as the present. We've now come back and had a combo of the two, where we can have continuous, steady-state processes punctuated by large catastrophic events. Not to sit on its laurels, being a big explosive system, it's also a big rotten system that keeps falling down. So in Canada, Meager is the site of the most large, substantial landslides. And in historic times, there's been at least 10. As I mentioned, highly altered rock over this 2 million year time scale. And what we're going to be looking at is this failure in 2010, on August, flowed down. Actually, there were some campers on a campsite where we always take our graduate students and undergrads when we're visiting Meager, which was slightly above where the mud flows went, because it was built on deposits from an earlier landslide, so it was slightly higher. But the campers basically heard what they thought were trains, but in fact it was the landslide coming down, and it just flowed around this little island that was their campsite. Forestry Road. Now, it's a massive event in 2010. Almost 49 million cubic meters of rock failed in an instant. Traveled, 50, 60 meters per second. Again, put it into scale. The Frank slide, which you probably all know, 30 million cubic meters. And that was a massive event. The Hope slide, even bigger, 47 million cubic meters. So Meagher's got that one done in spades. Again, we temporarily dammed the Lillooet River. Very, very temporary, a period of hours to a day or two, and then that failed and led to a lot of downstream flooding. It also generated, very much like St. Helens, the 1980 eruption, measurable, detectable earthquakes, magnitude 2.6, detected 2,000-3,000 kilometers away. So again, refresher, that was the big failure was coming off Capricorn Mountain. The big eruption was off Plinth Peak. And now we're going to zoom in to these FM1 and 2, very boring names for Fumarole 1, Fumarole 2. And there's actually a 3 now as well. I was very original when I was naming those. So the backstory, this time last year, reports started to come in of people in the area, guides, backcountry enthusiasts, and so on, and people working in the area as well. So these green spots are where we've mapped out people reporting smells of sulfur. So that real telltale smell is the rotten egg smell is hydrogen sulfide. You also can get sulfur dioxide, another sulfur species. That's the more common one that we think about when we look at volcanoes, but it doesn't smell nearly as intense. So they started to report those, and because of that, the seismologists at the Geological Survey of Canada and Natural Resources Canada went back into the catalog of earthquakes and started to drill in and said, well, do we see anything in the area? Now, the big problem is Canada doesn't have volcanoes, right? So the seismic monitoring was really just focused, and still is focused, on the earthquake issues, the next big magnitude 9 earthquake that we're expecting on the West Coast. So that means that we don't have the resolution to zoom in on exactly where these were happening. But they did see in their catalog, their archive, a swarm, an accumulation of earthquakes, fairly low magnitude earthquakes, between 2014, 2015, but nothing to hang your hat on. The gut feeling of the chief seismologist was, while the numbers were coming in at 40, 50 kilometers, we're saying now the base of the crust, his gut feeling was that probably they were shallower, but we didn't have the information to do anything concrete. And then luck comes along. So there's a helicopter pilot by the name of Hannibal Preto who's flying, helping scientists do a population survey for mountain goats. He's flying over Mount Meager, but as luck would have it, Hannibal had done an undergraduate degree in geology at the University of Victoria, and he'd taken a volcanology course with my colleague Dante Canil. So when Hannibal saw these holes in the ice and gas coming out, he knew them for what they were. He recognized that these were what we call fumaroles, where gas comes out of volcanoes. Either it's coming out of a big open vent, a big crater filled with lava, as you would think about in Hawaii, or more often, we think about some of the examples from Italy, you'll see these little vents with lots of native sulfur, very bright yellow, forming around them. Well, here we've got a glacier on top of it. Those gases have melted their way through. So Hannibal sent the pictures to Dante. Dante sent them to my friend Kelly at UBC. Kelly bumped them up to me. I sent them up the chain to NRCan, and we said, okay, we've got to get in there. We've got to go and have a look and see what is going on. Is there something new, or is this, we've just never noticed it before because people weren't up there? So we convinced them to come up with the money for a helicopter survey, and we did our first survey in August of last year. We took an infrared camera, a FLIR, and also a digital camera. The FLIR, we were trying to see, could we measure the temperature of the fumaroles? Unfortunately, those fumaroles are actually at the bottom of probably a 25 to 30 meter deep cave. So there was no way we could see through the gas. All we were measuring in terms of the temperature here in the infrared, maximum 20 degrees Celsius. That's the gas at the surface as it's cooled. I would be expecting 100, 200 degrees Celsius if we were actually seeing the vent itself. But the digital camera work, we were able to, again, like Yannick was doing for CX, build 3D models. This is a bit of a crummy presentation, I'm afraid, there. But there's one of the caves. There's another one just down here. And we were at least able to get some early estimates of the size of these things. As we zoom in, it's very tricky. There's no vegetation. When you're in these glacier environments, to get an idea of scale, it's very problematic. So each of these, this one here, FM2, FM1, and FM3 there, they're each about 30 meters in diameter, and again about 30 meters deep. So in September, we landed. So we got dropped off on the ice. Fortunately, I had two other PhD students with me, one Gio from SFU and Alex from UBC, both ice climbers. So they kept me from falling into these crevasses, and then I kept them from dying. Because they wanted to go into those craters. And they said, oh, wouldn't that be super? Let's go ice caving. And we've got our gas measurement equipment. It's a multi-gas that I built in the lab. And what we're in there is to say, well, let's measure the gases. Can we say something about what's coming out? What does it mean? So we went in, we slung one sensor over the edge. We're ice screwed in and everything. It was quite safe, relatively speaking. And here we are down from one of those. There's another tiny little fumarole sending out gas. But we measured up to 280 parts per million hydrogen sulfide, 2,700 ppm CO2. Now, just to put it into context, you can smell that rotten egg smell in the 2, 3, 4 parts per million. You can easily smell it. So that's why if you have natural gas at home, they put in a mimic gas so that if there's a gas leak in the house, you smell that rotten egg smell. It's not actually hydrogen sulfide that they're putting in. But the sour gas wells, here you'll smell the same thing. So we were getting 280. At between 100, 150 ppm, you start to get intense headaches, eye irritation, lung irritation. if you hit 1,000 ppm, you're into a coma on the first breath, and it's game over. Now, the problem with both hydrogen sulfide and carbon dioxide is it's denser than air, and it's invisible. And so in industrial accidents, many times what's happened is people have gone into low-lying areas, somebody has died, and they've gone in to try and save them, pull them out, and they've succumbed to the same problem. So there was absolutely no way that we were walking down in there, never mind going down into these caves. I was quite convinced. My sensor is still 3 meters above the vent, and I'm getting 280 ppm. In all likelihood, it's collected in this crevasse down here, potentially well over toxic levels. So I kept the students alive. It's a real problem if you lose a student in the field. The paperwork is just miserable. But doing interviews, myself and colleagues at the GSC allowed for other information to come to the surface. Reports from as far back as the 30s of people being up on the ice looking for hot springs and finding, smelling fumaroles. So we now know that this is not brand new. It's been doing this for a while. The question is, what does it represent? Is there a pulse of new activity, or is it a cyclical, long-lived change? So this is part of our ongoing research. Now, these big guys, why do we care? Well, they go pop. When they blow, their impacts can be broad and cover large areas. Some of these we've touched on, the gas hazards, these pyroclastic flows. Most lava flows are typically close to the volcanoes. But, as we've already mentioned, we can have these mud flows that can go many, many kilometers, serious landslides, and of course the volcanic ash, traveling hundreds of kilometers potentially. Human impact, well again, up near Meager, there's not a lot of people, but any life is important. People do spend the time trying to figure out what the cost of one life is. That's what the actuarial statisticians work on for the insurance companies a lot of times. But depending on wind direction, you've got well over 2.5 million people with extraordinarily expensive properties. I know my taxes came in this year. So, this impact is important on the human scale. It's also really important on the economic scale. As I mentioned, in Iceland, but also in Indonesia, some of these large events, we're looking at millions of people being stranded for weeks, hundreds of millions of dollars per day lost just in the airline industry alone. Conservative estimate, almost shy of $2 billion from one very small eruption where the weather was blowing the right or the wrong way. Normally that would have blown north and it wouldn't have impacted Central Europe. But there was a high pressure system pushing the winds down, and that's why we had this huge impact. So that's luck of the draw. The other big one that we're really dealing with at Meager is the fact that it's a massive rotten pile of rock. So the 2010, 49 million cubic meters is this area. Geo, who's been going back through the old aerial photography and using satellite radar data for current monitoring, has identified all of these areas in red that are also showing movement. And the one we're going to look at right now is this Plinth Peak. So the big eruption came down this side. The fumaroles are just right in there. And this area is scary because the data that he's got, we're trying to infill, but it was suggesting movement on the order of 5 to maybe 30 millimeters per year. But the scary thing is this. The estimated volume of unstable material is over 5 times that of the 2010 landslide, which was the largest historic Canadian landslide. So there is a significant hazard here. And, I hope there's no one from Energex here. I don't know how they got this in, but there's a run-of-river plant that is built on the Lillooet River. Many tens of millions of dollars of concrete. And it's basically just waiting to get clobbered by some of these landslides. So serious infrastructure, costly infrastructure. We can see going all the way down to Pemberton Meadows from the 2010 event. So anything 5 times larger, the impact is clear. So we are taking this seriously. There's active now, for the first time, we are, as of last summer, we are now monitoring Canadian volcanoes. I've been on a soapbox about this for about 10 years now, and we finally got off the pot and did it. So we've got satellite coverage, regular overflights. Satellites are great because you don't have to get out to the far north where it's expensive, inaccessible, and so on. And you can do it routinely and safely. So we're starting to collect a whole series of satellite data, and we can look to see, is that slope moving, or is that volcano inflating just before it's about to erupt because hot magma is rising inwards. Here's just an example of what we've seen just further south in Oregon. And this is being used regularly around the world now because it is so powerful. We have now got one seismometer on a Canadian volcano. It's still 10 kilometers from the area. It's at the site of one of these Energex power stations. But we'll get a second one going in hopefully later this spring. And we'll be able to at least start to monitor and look for any of those subtle changes. Seismicity and deformation are the two key monitoring networks that we use in volcanology because you can get them in and you can stand back and collect and get the baseline information that you really need to do to understand what's happening. We're making visual measurements. The helicopters that are flying over are now collecting images when they're in the area for, say, avalanche control, things like that. We will go back in this summer with another bunch of grad students and make repeat measurements of those volcanic gases to see, for example, is there a change in the carbon to sulfur ratio that can tell us about, is there new magma coming up from depth, or is it the old system just sort of sitting there ticking along, situation normal? So we've got to do the monitoring. But obviously, that's all great. You are not going to stop these events. So ideally, the monitoring is going to give the warning, but you need to do the groundwork to be able to mitigate the event. We're not going to stop it. We can do our best to reduce the impact. And so really it's a matter of starting to build integrated hazard maps where we say, okay, for this area, we see signs that we had landslides and we had bombs landing here or we had lava flows going there. Don't build there. Or here's the probability that it will happen in the next 10 years or 100 years. The same thing we do with flooding assessments, for example.